Okay, here we are in our introductory unit with lesson one, and today we're talking about measurement. Okay, and really, measurement deals with all those topics related to significant figures, metric conversions, rounding, calculations, and scientific notation. And so we're going to go through some of these topics and just kind of get them all out of the way. There's lots of examples in this lesson, so we're going to try and fly through them pretty quickly. Most of this stuff for most students will be a little bit of a review. So we're going to begin with significant figures. The number of significant digits in a value is basically the number of digits that are known with certainty. So this includes the following. So remember, we're talking about measurements. So anything in a number or in a value that's non-zero is significant. Any embedded zero is significant. All trailing zeros after a decimal, and any trailing zeros without a decimal if they're known to be measured. So let's take a look at an example. All non-zero digits. So in the measurement 1.234 meters, all these numbers would be significant. So there are 4 significant digits, and this would indicate that we've measured to a certain accuracy. We've measured to a millimeter accuracy. So this would be a very accurate measurement. An embedded zero, so anytime when we have a zero here that's embedded, this is still 4 significant figures. So this zero would be considered significant. Any trailing zeros after a decimal, so again, this measurement right here, 0.4000 millimeters, this would be a very, very accurate measurement, but these zeros are here for a reason. Okay, and the reason is that they're very, very accurate. Any trailing zeros without a decimal, if we specify that it's measured exactly. So 500 liters, with the word exactly after it, this would be 3 significant digits. If it wasn't there, then we would just assume that this is 1 significant digit. Okay? So here's an example. How many significant figures are in each of the following? So if we look at the first one, 527.3, well, these are all non-zero. These would all be significant, so there's 4 significant digits in this. 5,050 meters per second squared. Well, if we look at this and we were to see that, okay, well, this is an embedded zero, and these two 5s are non-zero, so there's at least 3. But what about this last 0 here? Well, if we know that it's measured exactly, and this is 5,050 exactly, then this would be 4 significant figures. If not, then it would be 3. So if this was written this way, I would argue that this would be 3 significant figures. 403, that's of course 3 significant figures. And last but not least, 0.0045 grams. This right here, these are leading zeros. They're not trailing zeros. So all of these zeros here are not significant. Only these 2 digits are. And so that would be 2 significant figures. So that you can see the difference between leading zeros and then trailing zeros afterwards. And there's a big difference because trailing zeros are significant, leading are not. All right. So now if we want to keep in mind these significant digits, and we're going to do calculations that have measurements in them, we have to know that whenever we multiply and divide numbers, the number of significant digits in the answer has to be limited to the number of significant digits in the least accurate measurement. So, for example, if you multiply anything by pi, you're going to get an infinite number of decimals, which in physics would represent an infinite accuracy. Well, that's not true. So we need to round our answers. And so we're going to talk about these calculations. And so what we have here is an example that will show us basically what we're talking about. So there's a carpet, and it's got these dimensions, 3.42 meters by 0.96 meters. And when we calculate the area of these, what we would do is that we do a quick multiplication, length times width, as you know, and we'd say 3.42 times 0.96. And the answer that our calculator will give us is this really long decimal place answer. And of course, we know that this is way more accurate than either of the 2 measurements that we were given in the first place. So we need to round this off. And so we say, okay, we need, basically I've got 3 sig figs here, I've got 2 sig figs here, so I need to cut this off. And so I do. And I say this is 3.3 meters. Okay, so basically that's the area of this carpet. And that's what we're going to do. That's basically the whole point of significant figures, is that whenever you do a problem in physics Your very last step is going to be to say, okay, I got to round this to the right number of significant figures. Okay, so when we're adding and when we're subtracting, the rules are a little bit different. We don't look at significant figures, we look at the number of decimal places. This is one of those conventions that's kind of a little bit silly, but we got to stick with it. So here, what's the perimeter of a garden with these dimensions? Well, we know the perimeter is 2 times the length plus 2 times the width. So we get 2 times 2.0056 plus 2 times 4.03. And when we do this calculation, what we get is 12.0712. And so now we say, okay, we got 4 decimal places here. We've got 2 decimal places here. So we round the answer to 2 decimal places, 12.07 meters. Okay. This is a little caveat down here. When we use multiplication and division with addition and subtraction, you just use the rules for multiplication and division. And for the most part, those rules, the ones for multiplication and division, are the ones that are the most important, because very rarely do we just add. Okay? So let's talk about rounding. There are some examples where rounding can get very tricky. It usually has to do with the fives. So when we round, we of course look at the figure following the one we want to be last, right? So if I'm rounding to 2 significant figures, then I look at the third figure, okay? If it's less than 5, I do not change the number, I just drop everything, okay? If it's greater than 5, so if it's 6, 7, 8, or 9, I round up. And if it's equal to 5, then I round to the nearest even, okay? So I round it so that the number's even. This again is a convention. So let's take a look at an example. So we're going to round these numbers to 3 significant digits. All right, so 2.1634. Here are my 3 significant figures, 2.16. Okay, so there they are. So I look at the 3. It's less than 5, so it means no change, so I get 2.16. Okay, so hopefully that's clear. So here's the next one. I get 4.0057. Okay, so 4.00, and I've got a 5 right here, and I've got a 7 after it. So what that means is that I'm going to round this. Do I round it up? Do I leave it the same, or do I just keep it? Well, this is 5, but it's got junk after it. So it's kind of bigger than 5, so I'm going to round up. So this becomes 4.01 kilograms. All right, 3.845. I'm looking to round this number, the 4, but it's got a 5 after it. So this is one of those examples where we're rounding to the nearest even. Well, this number's already even, so it means I don't change it. It just becomes 3.84 centimeters. All right, and our final example, so just so that you can see the difference, 4.235 milligrams. Again, I want to round to 3 significant figures, so it's this 3 I'm looking to round. 3 is not an even number, so this one I would round 4.24. Okay, so hopefully from these 2 last subsets, you can kind of see the example. All right, so let's talk very quickly about scientific notation. In physics, we very often deal with very large or very small numbers. So for example, Avogadro's number is 6.022 times 10 to the 23rd, where Planck's constant is 6.626 times 10 to the negative 34. So what those numbers indicate are numbers with tons of zeros in them, because they're talking about like really big or really small numbers. So instead of writing literally 23 zeros after this stuff, right? Scientific notation is the time-saving process, and we're just representing large and small numbers. So here's the rules. The first digit is always a number from 1 to 9. So here 6, here 6, okay? Then we write a decimal point, decimal, decimal, and then the rest, okay? Finally, we always multiply it by the appropriate power of 10. So let's take a look at how we're going to do these in an example. So let's write these numbers in scientific notation. All right, so we got 4.250 meters, 4,250. So we need to write this as 4.25. So what we need to do is the decimal place is sitting out here. So we need to move this decimal place over 1, 2, 3 spots. And when we do this, okay, when we move this decimal place over, now we need to multiply by a power of 10. So because we move it 3 spots, this is like saying times 10, times 100, times 1,000. So we write this as 4.250 times 10 to the 3 meters. Okay, so that may be familiar, and it should be familiar. This is very much a review. So what about 0.000980? Okay, so this one we're going to move the decimal place, but you'll notice instead of moving it this way, we're moving it the opposite way. So here we moved it to the left, here we're moving it to the right. And when we move a decimal place to the right, it means we're getting smaller, so we multiply by the negative power of 10. So this becomes 9.80 times 10 to the negative 4. Right? You'll notice that this trailing 0 is significant, as this trailing 0 was significant. So we leave that in. We don't round it off, right? We're maintaining the number of significant figures. Okay? So that's important. We have to monitor sig figs when we're using scientific notation. So let's take a look at a couple calculations. Okay? So let's do 4.02 times 10 to the minus 23. We're going to multiply that by 5.40 times 10 to the power of 5. Now, for many grade 11s, and hopefully this applies to not only the grade 11s that I teach, but also grade 11s, you haven't been allowed to use your calculator in math. And so what that means, though, is in physics, we're going to use our calculators all the time, but it means that you might be a little bit rusty with some of the neat little tricks that your calculator has. So we are going to use a calculator for this, to multiply these. We don't have to, but we're going to, okay, because really we're about saving time. So when we multiply these two numbers, first of all, we have to try and enter this number on our calculator, and we're going to have time in class to go over this. But the way that you would enter 4.02 times 10 to the negative 23 is 4.02, and then don't write times 10 to the power of, because you have a button on your calculator that either says EXP, or it says EE, or it says times 10 to the, okay? That button you would press next, and then you would enter negative 23, okay? And what that means is 4.0 times 10 to the power of 23, okay? And so when you do this, you should get an answer of 2.1708 times 10 to the negative 17. And now we monitor 3 sig figs here, 3 sig figs here. The powers of 10 do not add into our calculation of sig figs. It's just this number in front. So I need to round this to 3 sig figs. So I get 2.17 times 10 to the negative 17. All right, let's do another example. So try this in your calculator. 6.7 times 10 to the 28. Divide by 3.143 times 10 to the negative 7. And you should get 2.13172 times 10 to the power of 35. This has 2 sig figs. This has 4 sig figs. And so we round to 2 sig figs, 2.1 times 10 to the 35. Okay, so if this calculator stuff is not working for you, then we can come back to this in class where we're going to have an opportunity to practice. But until then, this is how you do it. All right, so let's talk about metric conversions. We want to talk about these quickly because they should be a review. You should have seen these in grade 10 science, in grade 9 science, probably in grade 7 and 8 science too. We have to be able to convert metric units quickly and easily. So this is a memory aid. I'm going to put this on your tests for you so that you know what these prefixes mean, so that you know what the symbols are, and so that you know what the meanings are. Okay, usually the ones in here are the most common. Right? You've heard of megabytes on your computer, gigabytes on your computer. Now we have terabytes. Okay, so you've heard of some of these. These ones in here are definitely the most, right? You've heard of kilometers, you've heard of centimeters, millimeters. You've heard of all these things, okay? Micrometers. So these values in here are probably the most common. They're the ones that we'll see the most often. But that's not to say that we aren't going to use very, very big numbers. And it's not to say that we aren't going to use very, very small numbers. And certainly we will use some of these in here when we talk about light, etc., etc. Okay, so there it is. And so these are what our metric conversions are. Now we have to learn how to shift from one to the other. Okay, and we're going to talk about that in a moment. But using this little guide is going to help you. It's because it tells you how big they are relative to the standard unit. Okay, so here's example 4. We want to convert 3.8 times 10 to the negative 7 nanometers into gigameters. And we're going to use this thing called dimensional analysis because this is a pretty big conversion to go from nanometers to gigameters. And if you look at that little memory chart, you'll see, okay, we're starting with nanometers. We have 3.7 times 10 to the minus 7 nanometers. And what we're going to do is we create this little crosshatch here. And we know that in every meter, if you look at that, there are 10 to the 9th nanometers. Okay? And so what we can do here is that we're going to cancel out these nanometers. We also know that in every meter, right, in every gigameter, there are 10 to the 9th meters. And so I've arranged these like this on purpose so that this unit, the nanometers up top, will cancel with the nanometers down below. Meters up top will cancel with the meters up top. And what we end up with is just gigameters. And so this, if you calculate this, 3.8 times 10 to the negative 7, divided by 10 to the 9th, divided by 10 to the 9th, is 3.8 times 10 to the minus 25 gigameters. Okay? This takes a little bit of practice. And if you don't want to use this method, you can simply add your powers of 10 and figure out what the answer is, which I have no problem with. If you have a way of converting units, use it, right? This is just a way that we can do this calculation and this figuring, and we don't have to memorize really anything. All right, so here's example, this would be example 8 in your note. Convert 200 meters per second into kilometers per hour using this dimensional analysis. Okay, so 200 meters, meters is up top, seconds is down below, meters per second, 200 meters per second. And so what we know is that there's 60 seconds in every minute. We also know that there's 60 minutes in every hour. And see how we've stacked these? The seconds up top are going to cancel with seconds down below. Minutes are going to cancel with minutes, and we're going to be left with hours. Now we got to turn this meters into kilometers. So we get, in every kilometer, there's 1,000 meters. So these meters are going to cancel with this. When we cancel all of these things, look at the numbers I have up top. I've got 200 times 60 times 60. And then what do I have down below? I've got 1,000. So 200 times 60 times 60 divided by 1,000 is 720. The only units that are left are kilometers per hour. And there's the answer. Okay, the last question is example number 9. Okay, and it's basically, this is a density question. A substance with a mass of 43.7 grams has a corresponding volume of 55.7 milliliters. Determine the density of this substance in the units of kilograms per liter. Okay, so we know that density is mass divided by volume. So we need to take this and this, values that are in grams and milliliters, we need to convert them and we need to divide. Try this question on your own. We'll take it up tomorrow in class.